Hey everyone, and welcome to this explainer. Today, we're going to completely decode your Class 12 physics syllabus and hack your way to top marks in both the HSC and MHT-CET exams. I am super excited to guide you through the mechanical properties of fluids. We're cutting out all the fluff, looking straight at the source material, and focusing on exactly what you need to maximize that score. Let's get into it. But first, let's start with a real-life mystery straight out of the Can You Tell section of your textbook. Seriously, think about this for a second. Why does a knife have a sharp edge, but a needle has a sharp tip? Well, the secret is all in the formula. Pressure equals force divided by area. By shrinking that area, making it super sharp, you're massively multiplying the pressure from the exact same amount of force. Grasping the hidden mechanics behind this one simple idea, that's going to help you solve almost any fluid question in under 2 minutes. All right, so here is our chapter blueprint. We've got pressure and Pascal's law, surface tension and capillarity, fluid dynamics and viscosity, a formula, rapid fire, board exam analysis, and finally, student traps. Section 1, pressure and Pascal's law. We're kicking things off with hydrostatics, the fundamental behavior of fluids when they're just at rest. Now, this brilliantly illustrates what we call the hydrostatic paradox. Notice how the liquid level is exactly the same across all these wildly different vessel shapes, A, B, C, and D. It's kind of wild, right? But it happens because pressure inside a static fluid is dictated solely by depth and gravity, not by the shape of the container or the total volume of the liquid inside it. If this pops up on your exam, here's how you get full marks. State the formula, pressure equals height times density times gravity, and clearly emphasize that horizontal shape variables do not matter at all. And that logic translates perfectly over to Pascal's law, which states that pressure applied to an enclosed fluid is transmitted equally and undiminished to every single part of that fluid. Think about a hydraulic lift. You apply a tiny force on a small area, like a master cylinder, creating pressure. That exact same pressure travels all the way to a massive slave cylinder. Because that second area is larger, your output force is literally multiplied. This is a super common 2-mark conceptual question. To ace it, always write the principle first and then the formula. Force 2 equals force 1 times the ratio of area 2 to area 1. Moving on to section 2, surface tension and capillarity. Let's take a look at the fluid's surface, where molecules actually behave like this tightly stretched elastic membrane. Okay, here is a concept that shows up year after year. The angle of contact. You absolutely need to memorize this technical definition word for word because it is a guaranteed board favorite for the short answer sections. It's defined as the angle between tangents drawn to the free surface of the liquid and the solid surface at the point of contact, measured within the liquid. Think of it like this, right? If you splash water on a freshly waxed car, it beads right up. That's a high angle of contact. But drop it on a really clean piece of glass and it spreads out flat, meaning a low angle. Comparing the physical outcomes of these forces is just fascinating. Look at the acute angle of a concave meniscus, like water in a glass tube. The adhesive forces between the water and the glass are actually stronger than the water's own cohesive forces. Now compare that directly to the obtuse angle of a convex mercury meniscus, where the liquid's cohesive forces completely dominate. Nailing the difference between these two states is absolutely crucial for crushing your objective questions. Section 3, fluid dynamics and viscosity. Time to shift gears to viscosity in motion and see what happens when our ideal and real fluids are actually flowing. Distinguishing steady, streamlined flow from chaotic, turbulent flow is your very first step to mastering hydrodynamic behavior. Streamlined flow is kind of like a highly disciplined marching band. It's smooth, it's got a constant velocity at any given point, and the layers never, ever cross. Turbulent flow, on the other hand, is like a totally chaotic mosh pit. It's irregular, super energetic, and just full of these swirling, erratic eddies. So what exactly turns that marching band into a mosh pit? It's velocity. Just like the textbook says, this transition point is governed by the critical velocity and the Reynolds number. Once velocity pushes past that critical limit, internal friction, or viscosity, starts taking over in different ways, dictating the exact moment this orderly flow totally breaks down into chaos. And that brings us to the absolute heavyweight of the chapter, Bernoulli's principle. For the supercritical 3-mark derivation of Bernoulli's equation, just follow these 4 logical steps that prove the conservation of energy per unit volume. Step 1, identify the work done by the pressure difference. 2, calculate the change in kinetic energy. 3, calculate the change in potential energy. And 4, just equate the work done to the total change in mechanical energy. If you structure your board answer in this exact sequence, you are practically guaranteed full marks.
All right, Section 4, Formula Rapid Fire. It is time to hack your memory with a high adrenaline review of the key equations and heavy hitter constants.
Let's kill some of that exam anxiety right off the bat. Never panic about memorizing these specific constants. The board paper explicitly hands these values to you right on page 2 for your numerical calculations. Just like we saw in the actual J837 paper, values like pi at 3.142, gravity at 9.8 meters per second squared, and Planck's constant are all right there. Your job isn't to memorize the numbers, it's knowing exactly where to plug them in. And speaking of plugging them in, here is the equation you need. Burn this formula into your mind. Bernoulli's equation. P plus 1/2 rho v squared plus rho gh equals a constant. It beautifully states that pressure energy, kinetic energy, and potential energy per unit volume will always remain constant in an ideal streamlined flow. Seriously, guys, this one is a massive CET and board favorite. Section 5, Board Exam Analysis. Let's get you that strategic advantage. We're going to decode the pattern of actual HSC board papers, specifically codes J287 and J837, to see exactly how you're going to be tested. You know, the board paper structure is incredibly predictable. It steps up from quick 1-mark objective hits in Section A to 2-mark short answers in Section B, 3-mark long derivations in Section C, and finally those complex 4-mark combined derivation numerical questions in Section D. Oh, and a quick tip for those Section A MCQs, always write the option letter and the correct text answer if you want to secure that mark. Let's look at the hard evidence here. Notice the pattern from recent papers. In paper J287, they tested the energy concept in Bernoulli's for an MCQ and then asked for a 2-mark derivation using Newton's law of viscosity. Then, in paper J837, they hit students with a 2-mark numerical on finding the coefficient of viscosity for glycerin. Viscosity in Bernoulli's? Absolute high-yield targets for sure. And actually, speaking of that exact numerical in paper J837, question 12 gave a horizontal force of 0.5 newtons to move a metal plate over glycerin. Successfully plugging this exact 0.5 Newton horizontal force value into Newton's formula for viscosity, which is F equals eta times A times dV/dx, was literally the only hurdle to unlocking a guaranteed 2 marks. It's totally plug and play, as long as you know the formula. Section 6, Student Traps. This is crucial. You have got to know the exact pitfalls to avoid so you don't bleed easy marks during the exam. Let's look at the biggest mistakes. Honestly, the ultimate exam traps are usually just careless errors. The number 1 killer? Forgetting unit conversions, like taking an area in square centimeters and just completely forgetting to convert it to square meters before multiplying. Number 2 is confusing gauge pressure, which is the difference from atmospheric pressure, with absolute pressure in your formulas. And finally, using an acute angle of contact logic when a question is specifically asking about mercury, which requires an obtuse angle. Don't fall for these. Well, we have covered the blueprint, everything from Pascal's multiplier effect to Bernoulli's conservation of energy. So, how are you going to apply this principle of conservation of energy to your own exam strategy? Are you putting your energy into the highest yield topics? Keep that streamlined focus, avoid the turbulent distractions of cramming the night before, structure your answers clearly, and I promise you, you will absolutely crush this chapter. Good luck, and keep explaining the world around you.